Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. Well, first of all, I want to say that I'm really honored and very thankful that we're having this meeting in honor of our colleague, Dave Notkin. Dave was a real gentleman. He was an excellent researcher and a wonderful mentor of students and a wonderful colleague to many people in our profession, including myself. So it's an honor for me to be giving any kind of presentation on his behalf. Basically, what I'll try to do today is first I'm going to look backward and remind us what program analysis, how we came to how we use program analysis, give a little history, talk a little bit about this paradigm that we've been calling blended analysis in our group for several years now, give you a taste for how it works in the context of a blended information flow problem, and then talk a little bit about challenges that lie ahead for program analysis. So in this audience, some of these beginning slides may be unnecessary, but I just want to make sure we're all on the same page. Program analysis, historically, compile time or static program analysis was developed to be used in optimizing compilers. And so the idea was you had to understand the potential behavior of a program and ensure that you didn't change the semantics of a program by any kind of transformation that a compiler might do. And so you needed to give a safe approximation of all possible behaviors, meaning you could return from an analysis a larger set of behaviors than the program had as long as all of its actual execution behaviors were contained in that set. So that's what I mean by a safe approximation. And historically, it also was used for checking program properties. On the other hand, dynamic analysis or profiling was used by many people to examine runtime behavior. So static analysis was done with the assumption that you only looked at code, you didn't have any information about execution time behavior or executions, but dynamic analysis was like instrumentation. It was tracking program behavior at runtime, and you could actually see things. So in the software engineering world, static analyses were used for various sorts of bug-finding programs or stylistic programs like lint, test case generation, and more recently, tools like dynamic testing and Java Pathfinder to try to verify properties of programs, and dynamic program analysis used for test coverage tools, for debuggers and things of that sort. So the community, the software engineering community, makes a great deal of use of program analysis. It's an enabler kind of technology for tool building. So let's not forget our history, lest we repeat it. These techniques were really invented or designed for languages like Fortran, okay? Pretty simple procedural languages. First, they started out looking at code within a function. Then they became interprocedural and dealt with programs that were sets of functions or or procedures. Things got more interesting when we gave up copy in, copy out parameter passing, which was pretty simple to analyze, and replaced it with call by reference parameter passing, because then you had the possibility of aliasing. That is, there could be more than one name for the same memory location to be accessed within a routine. And that's understanding the code a little difficult, kind of like memory locations having pseudonyms, if you will. Okay. And finally, people started thinking about analyzing programs, subroutines on different, or procedures on different invocations, and trying to specialize the analysis to the parameters of a particular invocation. Trying to use calling context to differentiate and make more precise analyses. We went forward into the 70s and heap structures, dynamically recursive data structures, and we ended up with points to analysis and pointers in C, which made analysis a great deal more difficult. And many people, including myself, published lots and lots of papers and done lots of experiments with how to get safe approximations of what a pointer might point to at a particular point at a particular time in execution. Onward into the into the 80s, looking at languages like Java and C++, I guess early 90s. Now we had object-oriented languages, and there was an interdependence of data flow and control flow, because the type of the object, which was the receiver of a method call, determined the target method chosen to be called. And so no longer could you think about the flow of data through a program as independent of the calling structure of the program, and that made things a little more interesting, but some of the work we did in points to analysis could be used in reference analysis. We also had to deal with the introduction of reference. That is, programs were allowed to ask questions of state at runtime and base execution on those answers at runtime. And so that introduces a kind of behavior in programs that's very, very hard to analyze at compile time, because you have to take account of all the possibilities for all the possible answers of the questions. And finally, we ended up with many of the modern scripting languages, such as JavaScript, which is what we're going to talk about today. And these are languages that are really almost intrinsically dynamic. They have dynamic typing, not static typing, so objects can actually change their type during execution. It's not class-based inheritance, it's prototype-based inheritance, which is much harder to model. And they incorporate a kind of a functional programming construct where you can actually not just load code dynamically from somewhere else, but you can actually create code by doing string execution time and then say, execute this. Okay, so this is sort of the real horror story, okay, to a compile time analysis, is to try to really figure this out at compile time. And in fact, you can come up with examples that are exceedingly hard, if not impossible. So let's look at JavaScript. This is a little JavaScript program. It doesn't do anything interesting. It's up here so I can show you what some of the dynamic aspects of features in JavaScript actually are. So we have this foo function, and the function is what we call a variadic function, meaning that it can be called with a variable number of arguments, which affect its behavior. Okay? And inside this function, we actually have an if statement where you can see two very different type of objects are created, and the variable z is made to point to either one kind of object that is created by a constructor A or another kind of object that is created by a constructor B. And B, two arguments, so we kind of figure out those are going to be properties or have something to do with the properties of the object, and A gets one argument, so clearly these are going to be different types. And then down in the middle here, in the second if, I have a dynamic dispatch, but this is based on the type of z. So we're looking at the bar property of the object that z points to, and since z can point to at least two different kinds of objects, we have no idea really what this bar function is. So we have type-based dispatch. This looks like Java, it's not. Okay, and the thing that's different is we can do an analysis at compile time that does a pretty good job in a language like Java or C++ or C#, figuring out what kind of objects Z can point to, because objects, when they're created, don't change their type, because Java and C++ are strongly typed languages. This language isn't. So the object it points to might be one of many different types, because the types can change during execution. More fun for static analysis. And finally, this is the kind of eval statement that gives headaches to people in static analysis, because prop 3 could be a property that's some kind of string expression. It could involve concatenation of values that are input. It can involve concatenation of things that are dynamically loaded excuse me, from another website. And without very sophisticated string analysis, it's hard to figure out what's actually going to be executed there. Fortunately or unfortunately, JavaScript is a language, and its siblings, I guess, things like Python, things like Ruby. Those kinds of languages are actually being used quite a bit, as in the bullets on the slide, in real website code. And they're being used because they're quite helpful to do the kinds of operations and the kind of base programming that people want to offer on websites. And we have several papers recently in the language and the software engineering community that attest to the fact, through dynamic analysis, that you can see evidence of these kinds of the usage of the dynamic features. So if we want to be able to enable maintenance programmers to maintain this kind of code, we have a program understanding problem. If we want to be able to test and have some confidence of the coverage of our tests on this kind of code as software engineers. If we want to try to figure out that the data integrity problem is actually being addressed, those kinds of problems that we normally do in software engineering in object-oriented languages are rendered more difficult in these languages because of their dynamism, because of these dynamic properties. Okay? So what's the answer? Well, one answer that we're trying is to reject the idea that we have to do everything in a safe, static manner and try to combine dynamic analysis with static analysis in a way that enables us to capture more of the dynamic behavior of these programs, save it, and then analyze standard static analysis that portion of the program that we have actually exercised. Okay, so that's the main idea. So blended analysis is a way to tightly couple an initial dynamic analysis, which is very lightweight and only records, in the problems we've been looking at, method calls and object creations, and to take those pieces of information and formulate a call graph that's annotated with that information, and then consider applying a static analysis for your favorite problem, points to or whatever you want to do, side effect analysis on that portion of the program. So it's not a safe call graph. It doesn't cover all the calls in the program. We're just looking at some set of executions we've observed. So what are the positive things about this? Well, first of all, we see all the code. Whether it's dynamically created or dynamically loaded or it was statically visible in the program. We have a dynamic analysis that collects the code at runtime. And secondly, we're actually able to do some pruning. That is, within some methods, we're able to try to specialize them for the parts that actually were executed during this execution. And if the executions are problematic, if they're associated, for example, with a performance problem that we don't really understand, then we don't care about the other behaviors. We just want to concentrate on the behaviors on this set of execution. And so that gives us a leg up, as it were, in terms of being able to be less approximate by the second phase of static analysis. And it also allows us to deal with dynamic program constructs. And so I want to show you some beginning work that we've done that we think is very promising in terms of how we can deal with these constructs. So first I'm going to show you a picture of a framework that we've built, and it's a plug-and-play kind of framework, so you can take your favorite static analysis and put it into the static analysis module here. And then I'll show you how we've instantiated it for the taint analysis problem, which is an information flow problem. So here we have a JavaScript program, and we have a dynamic phase, that is the dynamic analysis phase. The execution collector is a piece of the program. You can think of it as we're testing a website and we run the test suite and we do this lightweight dynamic analysis and collect the calls that happen for each test and what objects are created and where. And so we generate a set of traces and we send it to a trace selector. The job of the trace selector is basically to say, well, maybe we don't want to statically analyze the entire test, the results of the entire test suite. Maybe there's some redundancy in there. Maybe we want to pick out a subset and then try to statically analyze that subset and save us a little time. Okay. The second phase of the analysis, given some selected set of traces, is a big block I call static infrastructure, and I'll put more clothes on these. Basically, the building of the program representation from the traces and the walking of the program representation to do a standard compile time analysis happens here on each trace. And then we send it over to a solution integrator because we're looking at pieces of the program as we see them on these executions we've collected. So we need an module. I think of it as a generalized union to kind of combine together into a total solution for the program, for the part of the program we explored. So again, this won't give us the same thing as a safe static analysis. We're hoping it'll give us something more practical and something that will be more precise on the dynamic languages because we're able to observe some of the all of the dynamic execution on these test cases. So that's the overall put together of the framework. Now let me put some clothes on it in terms of how we do this for taint analysis of websites. So we have a website tester, and she is exploring the website by clicking on various URLs and various actions and buttons. And we actually are using a modified version of Safari that Jan Vitek's group at Purdue put together, and we changed some of the parameters to collect a few different things. And so we collect all the actions that are being executed, whether they're dynamically created or generated or not, and then we feed them into our trace selector. Okay. And I don't want to go into detail, but we have a heuristic basically that tries to make sure we cover as many dynamic constructs as possible, as many methods as possible, and as many kinds of objects that were created as possible in the program. And so we collect a subset of traces that will allow us to get that kind of coverage. And then we basically collect code from these traces. For each trace, we collect the code that we saw was executed, we build a call graph, and then we enter a vanilla static analysis, as you would apply globally if you did this all as a static problem. So to put a few more clothes on this, let me show you. This is the dynamic trace, and basically when you're on a website, you do some stuff on one page, then if jumps you to another page, and then it jumps back to the first page, and so forth. So we have a trace with sub-pieces from each page. Each one of these sub-pieces, to us, is what I'm going to call a page trace, and it consists of a calling tree, which is the tree of method calls that happened on that page, the dynamic code that we collect that was generated or loaded, as well as the static code on that page, and the object creation sites that we saw executed while that page was executed. So we take traces of this kind, these page traces, put them through the selector, and out comes a set of traces we're going to analyze. Okay, then the static infrastructure consists of these two pieces. We come in through the static infrastructure for each page trace, right? For each page trace, we take the call tree and build a call graph. We take the dynamic and static code we collected. We do a step called pruning that I'll show you in a minute. The pruning that is specializing code inside the method to this particular trace. And then what comes out is the code for that method we're going to analyze. Okay, and we do this piece over here for each one of the circles or functions that we're showing in the call graph. So here's code pruning. So here's a really simple kind of diagrammatic control flow graph, the flow inside of a method. We have two potential allocations and two potential calls. And the information at the top tells me that we only observed allocation 1 and call 1. So what that means is that allocation 2 didn't happen during this page trace. And what that means is we can get rid of that node and any nodes that are control dependent on the same conditions as that one. And likewise, we can get rid of the calls that didn't happen and any nodes that have the same control dependence conditions. So altogether, the stuff at the top is, I just showed you what happened in the code pruning piece. And then we go through a static taint analysis. And rather than detail about this, because I see I'm a little short, I want to show you results as well. Basically, the new stuff here is it's a plain vanilla points to analysis, but we use the dynamic call graph we observed, not an on-the-fly created static call graph. Those of you that know points to know that you're doing points to and graph construction together. This just says that we're doing a taint problem, meaning there's some user inputs, which are the sources, and we're trying to see whether there's some path in the program we can make it to between the sources and the sink, which is some kind of sensitive function call that we don't want this input data to be able to reach because a malicious person or malicious unit might send bad data there. This is just an optimization. We don't have to talk about this. And this is plain vanilla taint propagation on it, as you would do if you did a totally static thing. So we put together an experiment, an initial experiment, to try to look at pure static analysis straw men that we put together and our blended analysis. So static taint plot looks at the application code and the library code of these websites. Static taint minus just looks at the application code. Now what we used for the points to analysis was the best analysis that was available, which was a correlation points to done by the group at IBM and Walla, which is their analysis framework. It was talked about at eCoop 12. So all these analyses use that points to analysis. The difference is the static analyses use a static call graph. Our blended analysis uses the dynamic call graph that we built from observations. And we tested these two hypotheses, okay? How do these approaches differ in accuracy, and how do they scale, meaning how long do they take to do their analysis? So I had an undergraduate student sit and exercise 12 of the top 25 websites at Alexa when this work was done. She didn't know anything about the JavaScript code, so we thought that this is sort of a blind test generating test cases. This is the number of pages we actually had from each website that we exercised, and this is the number of traces, because remember, each trace is subdivided into subpieces that explore pages. And these are the results that we got in terms of accuracy. So you can see that the blended taint analysis, I mean, first of all, this is a sparse problem. It's a security problem. We don't expect to find, tons of answers. So only 6 of the 12 websites actually correspond. We actually found possible vulnerabilities in. The blended taint, the blue part is good. High is good. Here it means we found some source to sinks potential problems, and the red part shows the false positives. So the true positives were actually checked by hand, true and false positives, and the blended taint did a lot better than either of the two static taints, and in fact found 7 more true positives. 4 of them were in the dynamic code, in the code that the static analysis just couldn't see, couldn't deal with. 3 of them we don't know, because 3 of them were in the static part of the code, but we set a limit, like our points to analysis creator colleagues did. 10 minutes was considered too long, okay? So it was a 10-minute limit. If the points to analysis took more than 10 minutes, it failed, and we just didn't analyze that page, okay? So that was our level of scalability, which was borrowed from our colleagues. So we posit that the 3 that the static analyses didn't find, but were in the static code, potentially, if we let it run long enough, they might have found it. Okay, they should have found it, because they're both, well, at least the plus one that does whole program analysis should have found it. The minus one, which forgets about libraries, there's a possibility it wouldn't have. So here, blended found all true positives, additional 7, reported 1 false positive, and reported no false positives from the observed code. And this is maybe the more interesting result, which is the blended finished analyzing everything, and in fact did it on average in less than 60 seconds. The static taint plus, look at this, timed out at almost half of the pages. That was the whole point analysis and static analysis, timed out at the 10-minute point of over half the pages. And so here blue means that pages were analyzed, and red means the percentage of the pages that weren't. This is a scalability result, we feel. Okay, no free lunch. So what am I hiding? This is great. What am I hiding? Well, this is a security problem, right? And so, and this is an unsafe analysis. So let me just dwell a little bit on analysis theory here. I'm going to try to be as practical as possible. The ellipse on the left, this represents the solution that some pure static analysis would find. The ellipse on the right represents the solution that our blended analysis would find. The part in the middle here is the part of the solution found by both. Could have false positives, could have true positives. The part labeled number 1 represents part of the solution that maybe blended misses because we didn't explore the parts of the program that resulted in these exploits. So if we get good coverage, this is our hypothesis, if we get good enough coverage of the paths in the program, we'll make one as small as possible. And we're trying for good coverage of the calling structure in the program. Part number 2, and we observe this in our experiments, are the parts of the solution that lie in the dynamically generated or loaded code that static analysis cannot deal with. Okay? So static analysis cannot get this. And so what we are settling for, what we are suggesting, is that it's better to have a practical approach that will find you exploits in the dynamic code that static really can't deal well with, and in most of the rest of the program, knowing that you're using an unsafe tool, so there's no guarantees associated with it, but it's better to do this in a practical tool than potentially to get so many false positives or even time out after very long execution times in a pure static analysis. And that for those of you who know my career, this may sound like heresy because of the way I started, with my first paper being in Popple, but this is the future. These are the kind of languages people are using now, and this is what we're going to have to do. So we feel that we proved that both of our hypotheses are true, that we have an efficient algorithm. It handles dynamic features, at least the ones that we put in past. It's scalable to real-world websites. And in future, of course, we haven't really totally dealt with the dynamic typing. We'd like to make our analysis more precise and be able to tell when object types change and maybe change our answers in response to that. And so, and we also feel that it would be nice to know what family of other dynamic languages, like these scripts, like JavaScript, that are very, very helpful in programming today, we could apply these ideas to. And we feel that there's a lot of functionality here. And I've totally run out of time, so I'll just put this up. These were my attempt to try to think about future questions. I still think it's hard to deal with multi-language systems, multi-paradigm systems. Nobody really has a handle on this. And this is probably, as an educator, I think this is probably the most important question. What are about parallelism? We bemoan the fact that we're not teaching our students well enough how to use the 4 cores that are inside things like this, or the things in our pockets. And I don't think that the analysis community, dynamic or static, has really up with, you know, how we're going to deal with this kind of programming. And this is going to be the kind of programming that everyone is going to do. So that's the future. There's more to do. Questions? That is a hokey bird. Thank you. Danny?
So I'm not surprised that your blended analysis did so well. I'm surprised at the static. I was expecting that the number of the number of formulas would be even actually way much higher. So I'm surprised that it did so well, knowing how many unknown points and how many.
Well, these are the most popular websites. These are not. We're not suggesting these are programs that, you know, that the creators have not looked at. And when you look at these security problems, you don't find, it's not like looking for bugs. You don't find scads and scads of instances of these security problems. So I think that explains why there are exploits and not that many false positives. But each of the static methods had almost half of what they reported as false positive, which, as we all know, if you get half the, you know, that large a false positive rate, people lose incentive to use your tool, to use your analysis.
Did you find exploits in the libraries like jQuery and all these other?
These were just in user code. What we reported here was just in user code. We looked at the library, but we didn't look for exploits in it. The sources were not in the library, or the sinks. Yes.
I can see how this is incredibly effective for dealing with the valid code. I'm wondering how much it is about a val and how much is about dynamic features, like our variadic functions and things like that.
Well, I sloughed some stuff. What we do with the variadic functions is we introduce a type of context sensitivity. And so basically, every time you have an invocation of a function that has a different number of parameters or different types, we spew another node in the call graph. So we're basically effectively, by copying, making it kind of embarrassingly context sensitive, if you will. So variadic code, yes, but there are some other, I mean, as I said, we haven't dealt explicitly with the dynamic types. The points to analysis, we actually have in other work now that it's in submission, but in the work I'm reporting here, the points to analysis was aggregate, and there was one points to graph for the whole, for the whole page, for the whole program. So we think of a JavaScript page that's explored by several of these page traces put together for the same page as a JavaScript program. Yes?
Is there any relationship with the trace just-in-time compilers?
Oh, okay. I don't know. The trace-based compilers are looking for optimization opportunities, I think, not looking for. So I believe that if they translate code, they have to also keep the code semantically equivalent, but they're looking for optimization opportunities. So if they get it wrong, they just optimize something that's not executed very much. What I'm doing here is really missing some of the code, potentially. So I think there's a philosophical difference there. For compiler, for translation, this is not appropriate. But for some problems that are program property questions, this might be appropriate. Does that answer your question? Yeah. 3.
Three. Essentially, it seems that that would be an open set because you may have some input from the user. And did you in your experiment did you see convergence in this set? Like and you a bit more experiment, the set may grow.
What 3 was the part that blended, the part that's in the dynamically created part of the program that blended can capture, but static can't.
Sure.
We can only answer that question with regard to the state of the program at one time. If the program changes, then that picture would change.
I mean, did you observe that after so many times executing the software, this set is converging? Because this set would grow if it uses input from the user.
Take this line. We'll need to use pencil and paper.
Okay, let's go ahead and switch, and we'll have a discussion after this talk. So
Thanks, Mark.
because you bring those up.
Cool stuff. Can you all hear me?
Okay, so our next presenter is going to be Bill Sherwood from Carnegie Mellon, and he's going to be talking about. If this is not on.
Oops.
You can't hear me. It's the first time that's ever happened. Our next speaker is Bill Sherwood from Carnegie Mellon University, and he's going to be talking today about software assurance, particularly focusing on scalability and making sure that software assurance works on really large systems, not just toy examples.
Good. Thank you. It's very pleased to be here. It's and especially to speak with you about software assurance. And so, since I'm speaking about software assurance, it makes sense to start with the Queen of England. This is a natural starting point, and why is that? And so here's a hint. It's about software and assurance. Okay, so here's my hint. What do all these three things have in common? Come on now. Tony Hoare, thank you very much. Tony Hoare, who was knighted by the Queen, first computer scientist to be knighted by the Queen. And so some time ago at a meeting, at the HCSS meeting, Sir Tony made a comment to me, we treat our software as a phenomenon of nature. And I start with this because it carries two important messages about software. One is that, like other mysteries of nature, we will never fully understand it, and we will never fully control it. So these are really challenges of complexity and predictability. And this is a kind of a curious state of affairs, given the reality of software, which is we create the languages, the compilers and other infrastructure in which it's written, right? And we build the computers on which it runs. But we still don't understand it. And so Herb Simon's phrase, the sciences of the artificial, also applies here and evokes this. Now, there's some emergent complexity, but for larger systems, I think it's fair to say that that's a relatively small part. So the fundamental question for software assurance is whether this is somehow an immutable truth, that we will not make progress, or perhaps there's something that we can change. So I want to get past the sort of the reductive conclusion of, well, yes, both, and make an assertion today that we can intervene over time to undermine the validity of Tony's assertion, okay, and in fact make solid progress. So the reality is that the software assurance problem is getting both harder and easier, and I want to emphasize both, and Barbara's talk actually is the perfect lead-in because it is harder, because we are inventing these languages and getting ourselves into pickles that we maybe don't need to be in, but here we are. So I'm going to spend a few minutes trying to talk you into taking an optimistic attitude on this, that it is getting easier more quickly than it's getting harder. Okay, so here's the overall structure of my story, and it kind of boils down to how we can think as a community about how we might proceed. Now, those of you who've been around for a long time know that there are many dark lessons from the past. Those of you who remember in particular the 70s and 80s are probably the most ardent skeptics and pessimists in the room. And I was involved in working on theorem provers and verifiers back then and remember it well. But I would also say, like much of what we do in computer science, it's not so much what's new, it's what's timely. And I think there are a lot of ideas now that are timely that we can take up. Okay, and so in particular, we're seeing some benefits now from some new and I think really important technical interventions, and we're also seeing evidence actually of a strong business case, or at least a kind of an internal business case in which informed management has made a judgment to continue with the campaign of pushing forward with a range of interventions related to software assurance. And I'm particularly glad to be here at Microsoft to talk about this because they're way out ahead in both of these respects, both with respect to the technical interventions and also with respect to that strong case for internal adoption. They actually really do it. And so let's start with the harder part of the story. This is kind of a roadmap for our conversation. We all know that software is getting more capable in its function. It's more dominant as an engineering material. Is more critical or more critical in its role, and it's also more complex in its structure. And in fact, the National Academy economists, that's what the STEP committee is, said that software may be, and this was 2006, the single largest asset type in the economy. People who are involved with the F-35 estimate that maybe 90% of its functional features are manifest in software in one way or another. Software with wings is a phrase that was coined more than 15 years ago, actually. In vehicles, we're seeing a similar situation. The number quoted from industry is about 50%. And we also know that software is doing a lot more than manifesting capability. It's also a locus of flexibility. The software goes up into space after the satellite is already launched. And it's also a mechanism for linking things together. So, but we also know that the technical advances in software have had a big influence. Architecture matters, tools matter, process matters, and language actually does matter quite a bit, and both in positive ways. And Barbara, thank you for reminding us of the negative ways that language matters. So all these technical advances, and it's very important to recognize the role of the technical advances. They enable this kind of worldwide development that we see, for example, with Linux. This is the geography of Linux developers around the world. But more importantly, they have enabled these rich frameworks, APIs, rich supply chains for software. Years ago, we didn't have such rich supply chains. So if we look at infrastructure users, not so much Microsoft, but if we look at financial services and healthcare and everybody else, actually this tremendous complexity. And we've also gone, and this is a very important point, Butler Lamson years ago said about reuse, well, we do it. It's just a giant-sized components, operating systems, and databases. We've actually gone down now to much more granular reuse. And therefore, within our systems, we have these steeper gradients of trust, which means that our problem is getting more significant. We have attack surfaces within the systems, not just around the systems. And this is particularly challenging for the infrastructure users. Okay, so so these rich architectures it's really important to understand this. They're fundamentally compelling for developers. So an undergraduate building an app, a mobile app, can go from a gleam in the eye to an app in the App Store in a matter of weeks. Okay, that's the advance of our technology. Or if you just write a few hundred lines of code of map functions and reduce functions, you can go out and do and a few really nasty command lines. You can go out and do large-scale data analytics. And the ecosystem build on other advances. And so anybody know what the significance of this picture might be? I'll give you a hint. Zeus. So this is Athena bursting from the head of Zeus, which is how people think the iPod and iPhone burst from the head of Steve Jobs. But since Rick Rashid is being honored and returning to his work in operating systems, the Mac OS is in there in the iOS world. It's important to remember the heritage and the richness of the infrastructure. So now let me switch over to the easier part of the story and consider the broad timescale, going back to when I first met David Notkin, in fact, when he was a PhD student, Nico Haberman's PhD student at CMU in the bad old days of verification. And the easier story really has two related dimensions. One is the technical advancement related to a range of technical advancements, but particularly influencing our ability to scale up. And the second area of this easier part of the story has to do with process realism and tool advancement. I'm going to start with process realism and tool advancement because this is, in some way, the biggest shift from the 1970s. You know, in the 1970s, people who were thinking about formal reasoning looked at the waterfall chart and said, well, here's verification right after coding, and specification was done back there. So we'll start after the code is written and the specification is written, and we'll fill in that box with something that does something automatically. And that just was never going to work, okay? And the other thing about the focus in that time was on functional features of the system. And pretty much all the analysis we've been talking about here and in related meetings, to a great extent, really focuses on quality attributes. And there are a huge number of quality attributes. So with respect to this process realism and tool advancement, there are 4 facets that I want to talk about. So here's one of them, which is we're getting a lot better at advancing quality interventions earlier in the process. The whole point, if you look at the Libner-Howard SDL, for example, or the BSIM framework for evaluation of SDL-like implementations that Gary McGraw and his buddies cooked up, you see that there's a strong pressure to move points of evaluation as close as possible to the point of action that might cause the evaluation to be meaningful. And so this is NASA's version of the chart that you've all seen in many forms of how much more it costs as a function of how late you find the bug, right? Okay, and unit testing, we've got type checking, we've got service builds, and this influences quite dramatically the economics of overall cost, okay? So a second point here is that thanks to the tools, we've gotten a lot better at what I'm going to call incremental models. And this is a really important point that kind of has to do with economics of costs, benefits, but also uncertainty. Okay, and the idea of the incremental model is that an increment of investment yields an increment of return and right away. Okay, this is important because our processes tend to be iterative. And so in the iterations, we reduce uncertainty. That's a key feature of the iterative process. So in a sense, it has 2 pieces. One is that we can take small actions and get benefits for those small actions. And 2, the time from action to benefit is short, right? So the old model is I make a big investment of writing a lot of assertions, covering my program with invariants and pre and post conditions, and then maybe later I'll get some benefit for that. The new model is my action is a line or 2 of text, and then I get something for that. So I'm going to show you this little quote from the Chronicle of Higher Ed. I'm sure all you read this thing. Okay, and this was written by an English professor observing about computer science students as compared with English students. The English students felt that they needed to write the essay and get it right away and then submit it and it would be perfect, but not. And the computer science she was observing in a sort of a jealous attitude was they don't mind failing. They keep iterating and they keep failing. They do it all the time. It's built into the process and they take it in stride. And it's not that we somehow have become habituated to failing. Rather, we're really iterating. We're not failing so much as we're making incremental progress of a certain kind. We get increments of validation for our actions. We reduce the cone of uncertainty. There are lots of little benefits with respect to either the mean time to complete or the variance with respect to getting to completion. That's what happens in these iterations. And so we want to do the same thing with software assurance in our process. We want to get the assurance-related activities advanced as much as possible, integrated as much as possible. So a third point here about process realism is that our activities, our processes are now tightly integrated with tools, IDE-type tools for developers, team-type tools. We have now a data-intensive reality in software engineering, and we need to exploit that. Again, for folks who've been around for a long time, we're used to this impoverishment of data. Now we have masses of it, and we can do really great things to integrate all the various features. This is a tremendous increase in automation. So This is all from Mozilla because I can show it to you, but all the commercial systems kind of do this. Every line of code, millions of lines of code, its heritage is out there to be seen. Every little increment of change is accounted for. We've got extremely granular communications and interaction about issues. Without specifications, we don't know if they're bugs or feature requests. And we have this infrastructure for builds and tests analysis. If I click on one of these links, I get performance tests. There's lots of stuff going, like analysis, all this cool stuff, okay? And even some is a pitch for what I'm working on with, which is a sound static analysis to support reasoning about locks in Java programs. But there are a lot of examples of that, okay? So with respect to these tools, Watts Humphrey, who was the advocate of and a staunch advocate of process, for many years he was in the Edgar Dijkstra school of paper. So I don't know how many of you read those old Edgar Dijkstra screeds, but the originals were all handwritten, okay? And even Dana Scott, his papers were largely handwritten and discovered tech. And then of course, transformation. But in his later days, Watts actually recognized that for small teams, there's simply no way for the economics of developer time and attention to do the work without tooling. It's essential. Okay, and so finally, we can apply this incremental model to the space of quality attributes. And so this is the CWE, whether you like it or not. It's this huge inventory. It's got all kinds of category problems and the like. Just throw it at you as an example of the huge array of different kinds of quality attributes. And here's a tiny, I've just picked a few because I like concurrency. There's some related concurrency. My point is that if we can get granular with respect to these quality attributes, we have a greater chance of making progress, okay? Don't think about the whole thing as is it good or is it not, but rather think about sort of disaggregating quality into a composite. Think of it as a composite of a set of smaller attributes, and we weight the elements according to the context of use. Okay, so then, and here's some other examples of attributes which are kind of difficult to assure using traditional means of testing and inspection. These are kind of the natural targets for the kinds of analyses that Barbara is talking about and that are very much the focus of a lot of the tooling that's being developed at Microsoft. Okay. Okay, so I want to talk now about, so I've talked about process realism. Now I'm going to talk about some technical advances related to analysis and composition. I'm using analysis in a very broad sense. And the key point here, this is, by the way, a little puzzle for you while I'm talking. If you don't want to listen to me talk fast, find the bug. This was in Mathematica for years, undetected, in binary search. And if, you know, John Bentley did a study many years ago. He got all those hardcore AT&T developers for the switches, and he said, I've got an exercise for you. Here's 2 hours. Here's a blank sheet of paper. Write binary search. And they said, WTF. You can do this like that. Go out and have coffee. And nearly all of them were wrong. Knuth did a study. For the first 16 years, there was not a single correct version of binary search published in the literature. So even something very small like this is hard to get right. Okay, back to my point. All right, so some of the most important advances that we have made related to this broad notion of analysis have to do with composability. If you can't compose, you can't get to scale. That's just the iron law of our world. And so if you look at typing systems, you see that we have pulled it off for typing systems, but we are also increasingly pulling it off for many of those little attributes in that diverse array of attributes. This is a reason for optimism, but it's also a reason to keep working hard because it's not easy to get to that state of having composable analyses. Okay, ideally, and soundness is important. We want, let me get past this. We want, why is composability important, by the way? If you go back to these rich supply chains, All of these involve various bits of code. The granular business of providing little components, the glowing button that you want to put into the GUI that you pull off the internet, that little file, you want to build that into your system. Well, you need to be confident that that little component doesn't have extra functionality. That's the attack surface within. So in order to get to where we want to be with this, we actually have to accept some notion of fragmentary specification. And I would say Microsoft actually has pioneered this. But there are other examples. I mean, the use of JML. Tom Ball gave a talk recently about TypeScript. The point of providing these little fragments of specification is fundamental to getting to the point beyond heuristic and into actual soundness. No false negatives. Okay? And so my students, for example, when they work on the notion of annotation density, a metric of how much annotation do I have to write in order to get a certain theorem proved about the systems. So there are a lot of examples of technical advances here that many of you are responsible for. For example, things like type states and permissions and concurrency attributes and the like. And this enables these very rich APIs, the kind of APIs that let those apps get written, and to actually get some analyses targeted at those APIs. So you can keep getting more expressive and more rich APIs, but analyses that go with them so that you can be more confident that you're actually complying with the rules of the road. Okay, so I have to make a brief comment, and I'm sorry to inflict this on you, but about evaluation standards. I was at DARPA for 7 years. You get used to briefing fast. That was 20 years ago, but with the DoD, it's like the Hotel California. You can check out, but you can never leave. And so I keep thinking about these issues for them. And I have to comment, therefore, on the sorry state of the situation of evaluation standards relating to software assurance, because, I mean, there's a litany of woes here that I can talk about. I'll just name a few. One is they generally presume a linear process. They generally do an evaluation after the fact. That old verification model, you finish the thing, you deliver it off to an evaluator, and maybe a year will go by, and a lot of money will be spent before you get any result. And that evaluation process entails enormous amounts of reverse engineering. The information loss is prodigious. Think about these things, okay? And it cannot support things that we take for granted in the modern world of Agile and DevOps. Continuous evolution, changes of configuration, dynamic changes of configuration, component-based architecture, dynamic architecture, adaptive and resilient architecture. Okay, and it's not informed also by the kinds of modern techniques that we have for specification and analysis. Okay, so I mean, there's some excuses for this. I mean, good reasons for this situation. One is that these standards take years to ratify and get in place. There are just hideous consensus processes that have to go on in order to get, for example, to an ISO standard. They take a long time. So you want timelessness, and therefore you're going to get disconnected from the technology, and therefore you're going to get process focused, and you're going to get pulled away from the actual artifact. And it's the code that executes that matters. Now you say, well, think about the old Orange Book A1, if you remember that one. Formal verification. But what's the formal verification of? It's of properties of the specification. That doesn't actually sufficiently match the code. So fortunately, there's now a very strong message from the users saying that this state of affairs cannot continue. This is a great opportunity for the research community. It's a huge opportunity. The National Defense Authorization Act actually has a section in there, you can look it up, 933, which says, you guys got to get your act together on software assurance. So the real deal, they really recognize it. In 2007, the Defense Science Board issued a report saying, oh, the attack surfaces are within. Gosh, finally figured it out. That's great. And failure to maintain a lead in the ability to prevent and evaluate confers advantage to adversaries. All of this is a strong signal. NITRD, which is the coordinating entity for all the federal agencies, has a whole theme called Designed in Security. It's exactly about this stuff. Okay, so, got to calm down after that. So we have to kind of figure out how we can work within realistic guidance. I mean, the SDL is really baseline, and try to figure out how within that framework to get a little bit more product focused, a little bit more directly evaluating of the artifact. And the success of our, here at Microsoft, the challenge is how do we make that sort of more extensible and repeatable and build it into the expected pervasive baseline of best practice. All right, now I have to add one point about software just to reinforce the need here, okay, to address this carefully. And that is the most important point. We are not getting to a plateau in capability. Many of you remember there was a Harvard Business Review paper that came out about a decade or so ago. It said, with respect to enterprise IT, we have ERP, SCM, and CRM. Ask me later what they mean. And now we're done. For the enterprise, for IT. Search for sources of productivity and value elsewhere than IT. Okay, and what happened since then? Cloud, mobile ecosystems, machine learning, big data analysis, and so on and so on. Okay, we're not going to get to a point of automating programming. Now, I put this slide in the deck because somebody earlier was talking about getting rid of programmers through clever automation. This is a paper from 1958 by John Backus of one of the first Fortran compilers, automatic programming. Okay, now he was not saying we don't need no stinking programmers. That was not the point. That was the term of art at the time. But the idea of automating programming keeps coming back. 4GL's similar assertions were made. The AI crowd did it in the 70s and early 80s. And the point is the tide of abstraction just continues to rise, and there's no bound on that. And that's one of the reasons why our problem is both getting harder and getting easier, because we just keep getting more expressive. And so this, coming from Pittsburgh, I have to show you a sort of a steel kind of a shot, because it's not like steel. It's not going to hit some sort of asymptote as a commodity. Commodities sort of have these asymptotes. We don't have any asymptote in sight. So we have the chance, if I go back to the very beginning of my talk, right, whereas we control language, we control the infrastructure, we can just vector those things just a little bit. It looks like it's dynamic. It looks like it's doing eval, but maybe really not. Maybe we can actually have some analysis behind the scenes, and we can keep moving in that direction. And maybe I'm being ridiculously optimistic. Okay, so I have a modest proposal, and I just want to toss this out at you. And the idea is kind of very simple. And it's basically, let's build on a recognition of the process realities. Just to review, we're data intensive. We're moving forward with language modeling and analysis construed very broadly. And that we recognize the primary role of tooling and automation. Microsoft has this phrase, managed code. And the reality is, okay, I'm an Emacs user. I've been using Emacs since before there was Emacs. You know, nonetheless, if you really want to build real systems, you're probably not using Emacs. You're probably working in an environment with IDE and team support and various other. And that helps us manage and deal with all that data. Second is that we have a recognition of the emerging product. The role of architectures and APIs, the incredible complexity and power, therefore, of these frameworks that let 500,000 apps go into the App Store for iOS and 500,000 apps go in the App Store for Android, and I'm sure my numbers are low. Okay, and the importance of scaling through composition because everything connects to everything. Okay? All right. So also a recognition that with respect to our assurance techniques, taking a semantic bias is really the right thing to be doing. We're doing really great work with testing and inspection. But you know what? We can build tools to make inspection much more productive, right? To help answer questions that come up during inspections using analyses, even simple analyses. And if you use an IDE like Eclipse, it's very easy to get answers to those kinds of questions that might be asked and would otherwise be very hard to answer. To recognize the diversity of those attributes. The bad news is there are lots of them. The good news is each has its own story and we can make progress on many of them. To think about metrics that are actually based on analysis, not just counting lines of code or hours or what have you. Okay, and to use those metrics to reward developers for making progress in developing those fragmentary specifications and developing analysis results as well as developing code. And then really recognizing that the technical challenge of composition is fundamental. And finally, that if we don't think about the economics, we're going nowhere fast. And that was one of the big problems of the 70s and 80s. I'd like to talk about ROI. If I ask a developer to write one particle of annotation at not null, then that developer better get some benefit pretty much within the hour. And it can be a tiny benefit, but it's got to be enough of a benefit. And if it's not, something in the development process, it's got to be like an M&M or something, because that developer ROI is fundamentally what's going to make this all work and take off. Sort of this diffuse end benefit to the nameless maintainers from now is not going to go anywhere. I want to add this one, traceability. This is the hidden secret, I think. I think the great breakthroughs are going to be related to traceability. Connecting all these pieces and labeling those links and knowing which links are actually sort of semantic, what's the meaning of the link, which links are heuristic, enable me to focus attention, to use all that data and all those fragmentary specifications so that when I make a change somewhere in the system, right, if I add a component, then that helps me focus my attention to quickly get back into a state of harmony with respect to the fragmentary specifications and the analysis results. Okay, so that's the summary. Now, here's just a final wacky idea. I'm about out of time here. The final wacky idea is, and this came from the NSF Cybersecurity Conference, there was a session, and the session I was asked to chair it, and I thought, there's a crazy idea. Building codes. That's such an old idea. But if you think about a building code, the actual equities that are played out, you've got architects, people who are going to inhabit the building, people who are going to build the building, the people who are going to inspect the building. They're all these stakeholders, and they all are in horrendous conflict with each other. And there's a constant pace of innovation. And if you work that out and look at the process by which building codes emerge, you see actually there's some possibilities here. This is not a bad metaphor to consider. Has to be dithered a little bit, but it's not actually a very bad metaphor to consider. So that's the end of my story. I appreciate the opportunity to speak. I've got to say one thing about David Notkin, who was really an inspiring figure. Even when he was a grad student, those of you who were at CMU at the time remember how inspiring he was then. He really had 4 characteristics. He had a strong vision. He showed respect for data. He showed the value of working hard to get some data and then the need to analyze it correctly. And he also had respect for semantics and really doing the math. Right? We do great math, but we got to encapsulate and hide that math, awesome as it is, for our users because they don't really enjoy it that much. Right? And finally, a willingness to push to change the paradigms. And I think that we can appropriate these lessons to this activity. I think the time is right. I think we really have an opportunity to disrupt in a really good way if we think in the right way about our practices and our tools and our languages. Thanks very much.
Okay, so we have time for one question. Can I have my panelists come up and sit at the table while we're answering it?
Yes, Kevin.
I wanted to kind of get your response to a proposition that computer science is on a collision course with systems engineering. You see this most particularly today.
That had to be the one question?
With respect to cyber physical systems.
Yes, yes. Let me clear this out.
In that realm, it's not just software behavior that matters. It's affordability, adaptability, dependability, usability, interoperability. How do we get from where we are to the point where we can be comprehensive of the key abilities of complex systems that are so heavily reliant on software?
So that's a really hard question, and I would be disrespecting the panelists if I tried to offer a full answer. But what I will say is the bottom-up attitude is a really good attitude to take. And the bottom-up attitude is figure out what we can do with the data that we've got, what little tweaks we can make to get some additional bit of assurance. Okay? And pick those ilities off fragment by fragment. And I think that's the right way to go. That's incremental progress for the community. Okay? And we'll see the rewards in practice. And those who observe those rewards in practice will reinforce that system. Okay? And that's really, I think, the way we've got to go. But the other point about systems engineering is you got to pay attention to the actual technical realities, the semantic stuff that exists in the world of software, because it's very different from the other disciplines that are integrated into the systems.
Okay, great. Thank you for a wonderful talk. So next on our agenda is a panel. So the way this panel is going to work is that each of my panelists, we're missing a panelist. Oh, there you are. Sorry. I can count but not pattern match. So each of the panelists is going to get about 5 minutes, and I'm going to hold them to it, to present some ideas about their vision for the future of software engineering. In particular, what are the big open directions and open problems that we need to be solving. And then we're going to open it up to questions. And the questions will be to them or to anyone else who have spoken or to anyone else in general. Ask big, important questions. Some of them have slides. So why don't we start with David, since he is on the edge? To talk from here.
How do I advance?
In a second, you can advance here.
Okay.
There you go. You can advance from here.
Do I get a...
Thanks. So it's an almost impossible thing to do, is to talk meaningfully about open problems in 5 minutes, but I'll take a quick crack here. As I was thinking about this, one can look at open problems in terms of very specific things or very general things, and I'm trying to pick something here that I think is an emerging trend, and we can actually see it in many of the talks that we've heard today, and that is a shift from focus on development time to runtime. So the problem is today, as our systems get put out there and become relied upon, that we have requirements for high availability and performance, even in the presence of lots of changes around the system and inside it. The environment, various kinds of faults, different changes in user needs at different times, system upgrades, human errors, and even maliciousness. And through all of that, we would like to do this in a way without costly human intervention. And so this leads to a natural conclusion that what we need are systems that can be, that we can begin to use systems and techniques from development time and put them in the runtime. And let me just give some examples for that. The basic idea here is to migrate many of our techniques to runtime and automate their use. And we can see lots of examples of that. Quality assurance, for example, which we think of as a time during development where we find bugs and where we determine whether the system has the properties we want, can be done in terms of runtime diagnostics and testing. Architecture manifests itself in many ways at runtime through, for example, runtime architecture-based self-adaptation, or techniques for actually adjusting qualities of service dynamically, making trade-offs that would otherwise be fixed at architecture time. Analysis, things like runtime model checking and simulation, and requirements where you establish new goals at runtime and work them out as sort of system changes. We can see there's actually examples of research in all those areas going on, but I think it's important to realize that this is a big shift in the way we think about software engineering. And as I will skip over my examples of this because we don't have time, that in general, one can pose a whole family of interesting research open problems, which says, take your favorite design time technique and ask yourself, how could we deploy this in a runtime setting? You'll find that when you do that, there's typically a reasonable idea behind it, but in fact, there are some fundamental changes you have to make in order to be able to deal with the real-time nature of decision-making with some certain kinds of uncertainty and so on. But once you've done that, then there's a lot of other problems that arise. For example, how do you have assurance about these things that are happening at runtime and actually changing the system? How do you actually improve the adaptations that are going on and the performance of the things that you've put into the runtime? Mixed initiative control, we heard today in a couple of the talks about approaching the user and being able to work them into the system. And that introduces a kind of non-determinism into the whole problem that makes it really tricky. How do we design our systems so that they have the right control surfaces for the adaptations we want to make? Proactivity. How do we look forward in terms of the adaptations instead of just reacting to problems, but actually anticipate what they will be and fix them? And in general, being able to take control systems, ideas that have been around for years and years, and be able to pose those in the context of software-based systems where you no longer have differential equations to help you out here. So overall, the general point I want to make is simply that there's a very large class of very interesting open problems hiding under this whole business that we're moving towards, where we take static development time techniques and move them into the runtime.
Yeah,
and then let me just stand over there and talk.
that's exactly what I'm going
Thank you. All right, I just have one. How do I turn this on? Hello? Okay. All right, I just have the one slide, and as you can see, it doesn't really say much of anything. Well, it turns out what I'm going to say is more or less what David said in but in a somewhat different way. My slide shows my affiliation and my lab's logo. The important thing about the logo is, it says we enable. And it's really not just my lab, but it's the software engineering community and also the programming languages community. What we enable is software, everything about software that all other software-related communities build upon. And fortunately, we're sort of always thinking in terms of building. We're focusing on building. We're focusing on design time. We're focusing on development time. And basically the same thing David said is I think the thing that we need to do is not be such an idealist that we're going to get it right the first time and get it out into the environment and deploy correctly, but be more like, I don't know, some of the people I've met. We have in my department at Columbia now some people in operating systems, some people in security who are doing what looks to me exactly like software engineering, except they're doing it at runtime. They're doing it in the deployment environment. And I think we need to do that too. In fact, the reason they're doing it is because we didn't do it, because we didn't get it right. And we're never going to get it right. No matter how much fun we make software engineering, no matter how much context the software developer has, no matter how much science we bring to bear on it, we will never be able to prevent all bugs, all vulnerabilities, and so forth. We'll never get it right the first time. So there will always be bugs, and we have to become pragmatists and be able to find them at runtime and deal with them at runtime. And that's all I had to say.
Thank you.
And who do I pass to now?
Okay, no slides. In a novelty for this technical discipline, you're just going to listen, not watch. I do have a slide. All right, it's got my affiliation. I want to make 2 points, one about an engineering discipline for software and one about software research methods. I really want to not respond to the individual talks today so much as go back and touch base with the idea that if we're going to call it software engineering, we ought to take seriously the proposition that we're striving to build an engineering discipline. So to touch base with that idea, let's look at the definition of engineering. There are many, but they boil down to this: that engineering is an activity about creating cost-effective solutions to practical problems by applying systematic codified knowledge to building things in the service of mankind. And definitions of engineering pretty much have those clauses in them. Now, those practical problems are situated in the world. In the world at large, there are vastly more people who are not highly trained computing professionals who are not only using computing, but who are tailoring computing to their own needs. And we are doing a dreadfully bad job of giving them systems that they can understand and that they can manipulate either to their satisfaction or without risk of safety to the public. So Laurie showed us some examples from medical processes where they can take ideas from software engineering into an application domain and in terms of that application domain make real progress. But we have a desperate need to make our technologies comprehensible, accessible, manageable by people who are not like ourselves. And I want to call that out as the huge research challenge and research opportunity. Another clause of that definition is about systematic codified knowledge. Well, Mike asked, where'd Mike go? Mike asked, when are we going to take away control? And my answer is, it's high time to take away control of some of the details that don't matter that much. You know, I remember the conversion, the great leap from assembly language to higher level languages in around 1960, the early 1960s, maybe up to 1970. And one of the big objections was, if you only give me 3 loop structures, I won't be able to write all the loops that I've got now. And you know, it turns out that for the most part, that's okay. So gratuitous variability and its associated costs and maintenance lead me to say, yeah, we should start taking away control. So systematic codified knowledge in the case of engineering means engineering handbooks, means building codes. Bill talked about building codes. This is about taking the things that we know that work in the routine cases and getting them organized so that we can just go on about our business and worry about the hard stuff. We could do a better job of that. Prem said that exact models may not work. So we all have an urge for well-founded theories, for exact analyses, for complete proofs of the entire specification. And at scale, in the real world, in practical problems, that's not practical. One of the ways that we've dealt with that is with empirical statistical models, but they don't lend themselves that well to explanations. If you look at the engineering world, they really like linear models. Not all the phenomena they describe are linear, but linear models are mathematically tractable, and they're good enough in most cases. In addition, we don't need to prove everything. What we need to do is to show, as Alex was saying, that we're getting the right outcomes, or we're detecting that we're not getting the right outcomes, but without worrying about all the details of the ancillary activities of the systems that don't actually matter that much. So here again, so as with making computing accessible to real people, we need better abstractions that work for them. We need better abstractions about systematic codified knowledge that work for designing and developing systems. I say again what I said earlier, that I think we need to break the bonds that tie us so strongly to the code and think about the systems as a whole. Bill talked about supply chains. That's one way of doing that. So we're engineering software systems. We need to take a systems view, and we need to find abstractions that will let us work at the system level for that purpose. So with respect to an engineering discipline for software, I think we have lots of opportunities to focus on finding abstractions that work for us, that work at a high level, and that make our systems comprehensible not just by us, but by other people. Now this is Fuse, not Fuse research, but we are here mostly researchers, and I want to take a minute to talk about opportunities in research methods. So Laurie talked about methodologically defensible research plans, and we had a short exchange this morning about the state of research in software engineering. And as I said then, I think we have progressed in the last decade, principally by understanding a handful of particular research approaches, the most conspicuously being empirical methods. But that doesn't exhaust the needs of the research community. We have a lot of different kinds of problems that we solve. We use a wide variety of different research approaches, from formal mathematics, through statistical empirical work, through human investigations, through qualitative design and methods. And so to have a research methodology that works, you need to be able to identify a matched set of a research claim, of the techniques you're using to investigate that claim and produce a result, and of the evidence and the validation. And I emphasize a matched set because some kinds of validation work for some kinds of claims. I repeatedly have discussions with PhD students in which they say, my claim is da-da-da, all da-da-da-da-da, and I'm going to do it with an empirical analysis. Well, sorry, if you want the universal quantifier in the claim, you're going to have to do something formal in the method. So we need to understand better what constitutes a matched set of claims and methods and validations. so that we as researchers and that we as reviewers and that we as members of program committees can generate methodologically defensible research strategies. Much remains to be done in that area, though I think we are making progress. So there's 2 points, one about an engineering discipline of software and one about research methods for getting there.
So I'm the virtual Tom Ball. Tom had to leave early and he asked me to stand in for him. I have 2 points to make about sort of promising directions for software engineering, one of which is the point that Tom was planning to make, which I'm wholeheartedly in agreement with. And the other one is my own point, which I don't know whether Tom agrees with or not, but we'll assume he does. The first one, which is the point Tom was planning to make, is that there's a extremely promising opportunity for the research this community does to take advantage of the cloud. And I can sort of talk to that very directly because about 1.5 years ago, Galen Hunt and I started a project inside Microsoft called Cloud Build, which was an attempt to get developers to stop building software on the desktop machine, move to a cluster of machines in the cloud. You know, many of you know Google already has this. They're very successful with this. It's a great idea. You know, obviously, there's lots of things that could be done in the research community. There are 2 things I have to say about it, one of which is that something happened with this idea that I've never seen happen before inside Microsoft. We wrote a white paper, we circulated it around, and developers from the rest of the company were so excited, they volunteered to come over and help us in research to build this. Usually, it's the other way around. We're going over and begging them to look at something that we've done. We had a white paper, and they were volunteering to write code. There's a huge opportunity here to improve developers' lives by basically accelerating the process of building software. That's only the tip of the iceberg, though. The reason that I was particularly excited about it is that once you've done that, you have all of the artifacts and the beginning of the tools living in the cloud. And a lot of good things come from that. One of which is that other parts of the software lifecycle can be moved onto this platform and done in parallel at very large scale. Testing is the obvious thing to move next. Tools are another thing that benefits from this. And so why is this important? Well, one thing is that all of a sudden you can start sharing artifacts of all of these processes at a very fine grain. So when I build something and Bill comes along and builds something and he's changed one file, he could take all of the binaries that I had, with the exception of a couple of them, and just reuse them. So instead of running the compiler again and doing redundant computation, we can just accelerate the build process. Now, for building, you know, that has large advantages, but imagine how much it has for advantages in other parts of the process which are even more expensive. Testing is more expensive than building in general. Static analysis, if you're doing it across the entire program, is even more expensive. You can reuse large parts of these analyses or these builds or these tests across users. Second thing is that you've all of a sudden got everybody running on a common platform. And all of the things that are important in terms of developing software with a community and a process are a lot easier to do if the software is not living on machines and people's desks in their offices that are sometimes turned off and so forth. You can see across an entire project, which is why lots of people in the company are extremely excited about this prospect. Wolfram Schulte, who many of you know, has actually gone off and built a team outside of research to build this idea out. So that's the sort of one interesting direction I recommend to this community. The second thing, which I'll say, is that I heard a lot of talks today about sort of going and building tools for helping people build software the way we already have built software. I have to say that there's another way to look at this, which is that we need to teach people how to build software better than the way we build it now, and not go and sort of try to patch up the software that we have and try to find the bugs in it, but instead try to help people write software that has fewer bugs or that is intrinsically more secure. Give you a concrete example. A few years ago, Galen Hunt and I built an operating system called Singularity. It had 2 sort of very important features for this community, one of which is entirely written in a high-level language, C#, so buffer overruns, that type of attack, just totally prevented by the type system and the memory safety in the language.
Second thing is that we thought about the architecture that was made possible by having safe languages. And we built something that was far more contained and isolated than today's systems. So everything lived in its own process all the way down to the device driver level. Processes only communicated across channels, which are effectively capabilities. And so we had an operating system that was fundamentally more robust than what you have now. That is the kind of thing that actually changes the way people look at software and build software. Is it perfect? No, of course it's not perfect. We had bugs. We knew that. But it changes the way people, it just sort of starts people at a higher level than they were before when they're writing in C or something like that. And so, in particular, when I look at something like the mobile space, where we had this clean slate, we didn't have any backward compatibility, and I see all these people writing in the same old languages, using the same frameworks that we had just ported over, and having the same bugs, the same attacks, the same problems. I'm very discouraged that, various communities, including this community, didn't say, let's go, let's do it better, let's learn from the mistakes, let's try to produce software that's just fundamentally better by design. So that's what I say.
Thank you. Okay, so I would now like to open it up to questions, and I'll let the panel decide who's going to answer our question.
Just like to make a general observation about the talk that we heard today, and curious because just right before the last panelist talk, I would say that basically being heard about possibly new solutions to very old problems or well-known problems. Nobody was talking about new solutions to possible new problems that are going to face in the near future because of the change in hardware, great systems. There is a wonderful panel in the faculty summit like Monday was how changes in the hardware ecosystem will disrupt computer science. And it seems that for us, this change don't concern us at all because we only talk about old problems. So the last time we made this point, like we can move everything to the cloud, to change new great systems. We are facing new problems we are not talking about today. So my question is, are your views on this possible? The fun of talking about the future is trying to predict. We always make mistakes. But which kind of new problems are going to face in the new future that we don't even know about, or we don't even worry about today.
So the future of software engineering problems. What do you guys think? Someone else want to?
Well, I'll take on a little piece of it, which is the notion that we have of checking and correctness. There's been an evolution from my program has a specification and it is correct, which is applicable to things that are small enough to be practical, to be tractable. And as the problems get bigger and as they get, particularly as they get embedded in physical systems, where the physical systems don't themselves have repeatable behavior, we need to adapt our understanding of what constitutes an acceptable program from the theoretical model of correct to the model of it does what I need to do right now. And that involves having criteria that reflect the context of the problem as well as the system that's solving the problem. It involves having approximate models that are mathematically tractable, that you understand may not be exact, but they're good enough for practical purposes. I think there's a lot of opportunity in that arena.
One thing I'd like to say, with sort of related to the same idea, and this is sort of getting at what I was getting at before, is that we're not going to get everything correct. We're not even going to know what is correct. I mean, that was, I think, your point. That once we get to cyber physical systems, what?
Especially in the fringe details.
Oh yeah. We're never going to have complete specifications for a lot of these very complex systems, particularly like as Mary mentioned in cyber physical arena and so forth. And so we have to, deal with the reality, and that was what I was getting at with respect to some of my, colleagues in operating systems security. They deal with the reality all the time that there will be a break-in, there will be a system crash, and they have to figure out how are they going to work around it, how are they going to deal with it in real time when it really happens. And I'd like to see more of, our community working in that area and applying software engineering kinds of mechanisms to what really happens at real time at deployment. And then, use it for feedback. Use it to go back to the development lab and make patches and, and changes and so forth, rather than just, a patch on the fly and then forget about it. But, we have to deal with the reality of things going on.
I was going to mention cyber-physical systems also because I think having started to work in this area, one of the problems is you run into system development efforts that involve totally different communities with completely different perspectives on what it means to go about designing a system. And yet they all have to somehow come together. So reconciling physical models or control simulation models with software protocol models, it's not clear at all how to do that. But I think it's something we really need to address. And somehow I don't see much of that going on here in terms of broadening our own ideas of how to reconcile the kind of things we know well with the things that they do well.
About a very tension evolution and revolution. Right? So these things are competing with each other. I want to hear your thoughts. If you want adoption, then probably you want to do it in the evolutionary style. If you want creativity and new breakthroughs, are these things at odds? And you could never have the benefits of both worlds. Is there a way in which you can get adoption and as well as new breakthroughs, new
right.
New ways of
No, I mean, your point is well taken, is that it's complicated when you bring out a new, let's say, device like a mobile phone and you decide you want people to program on it. But the larger picture point, I think, is that there were no good alternative models developed by the academic community that would have said, if a company, let's say Apple, had wanted to do better than what they did, what would they have done? Were there well worked out models that had been studied over many years that seemed to offer promise that they would have been considering whether they wanted to take the risk in that space or not? And I would argue that there weren't those models. And so there was an obvious thing to do, which was to continue what you knew how to do and use the tools that you already had. And that's lower costs, but there was nothing to balance it against it. And that, I think, is the unfortunate part. And that's what I think academic researchers can particularly bring to the table, is the ability to look at these problems further out in a context that's not as tied to product deadlines as people in companies are.
Danny's comments actually resonated with me with respect to what Mary said as well, because she was talking about using an engineering discipline, and to adopt the Kuhnian metaphor that you took, there's normal science and revolutionary and paradigm shifting science, and we should always be using principles when, even in the paradigm shifting, but we may not have the same sort of codified body of knowledge, a book we can just look up in those situations. Actually, if you want to react to that, you can. I had something else I wanted to say, too, though.
Okay.
So I wanted to react to what David and Gail said about moving more of our activities from design time to run time. Another way of saying that is, whenever you have a static analysis, why are you doing that analysis statically? Shouldn't you be doing it dynamically instead, or as well? And I think that makes a lot of sense. I think that in the future, all successful analyses are going to have components of both. Because when you look at dynamic loading and meta-programming like reflection and multilingual systems, it's going to be very difficult to analyze them purely statically. But I wanted to bring up two concerns about this that maybe first is that I think we have to recognize that whenever you move an analysis from static time to dynamic time, then you are abandoning the guarantees and understanding the system.
I never said move it. I said do both.
Okay. So
I never intended to say stop doing the things we're doing now, but I was saying we, in addition, need to do these other things because, we're failing. What we're doing now is not sufficient. Okay, and so we need to look at doing something else.
I agree with that.
Well, I don't quite agree with that point because if you take, for example, systems that produce an adaptive layer that attempts to react to problems in the system in a control systems kind of way through monitoring and then actuation, you can analyze the control phenomena and the programs that are in that, even though they're running at runtime. So many of the adaptation techniques that are being used there can be guaranteed to do the right thing at runtime. So I'm not sure we're abandoning completeness or assurance there.
That seems like one very particular type of software. I mean, if we think about the set of all software, that's a small part of it. And the fact that you can get some kind of guarantee there, even with even though you're doing runtime monitoring, seems of value. But it also seems like you wouldn't want to apply it blindly everywhere. Or at least if you did, that you would recognize what you're giving up.
Well, for sure, you don't want only do that. I agree with that. Right.
So the one point was a concern that you're gaining tremendous precision, but you're losing these guarantees. The other thing is that I think we should also be thinking about going in the opposite direction. Whenever you're doing an analysis dynamically right now, whether it's being done by the runtime system or by a check that the programmer is doing, or by a higher level monitoring system, we should be asking ourselves, why aren't you doing that statically? That is, in addition to taking everything we're doing now statically and trying to do it dynamically as well, we should be taking everything that we're doing dynamically and try to do them statically as well. Because they'll be more conservative, they'll be less precise, and they'll give us certain guarantees. Guarantees in terms of behavior, improving the understanding and structure of our systems. And so I think we really need to be seeing that sharing going both directions.
I want to respond to that. Part of my argument was not just we should do things dynamically, but we should also do things in the deployment environment, which means with the real users, with the real data that they are really working with. And yes, that can feed back to, static analyses, but what we have to deal with right there is the actual dynamism. Running the static checks and so forth in their environment may not really make sense. I mean, it makes sense to use the same environment, but the overhead and so forth may be inappropriate. In fact, that's something to work on. That's another topic to work on is, what can we do to make it plausible to run those static checks in their environments in real time while they're doing things.
This should not be just about static and dynamic analysis of code. If you evaluate a piece of code in isolation, then in order to make guarantees, you have to make guarantees that are applicable to all the contexts of execution. And so some guarantees or some analyses ought to be done in context because the context establishes the properties that actually matter in that particular setting. And by focusing on those rather than having to validate all the properties, you'll focus better and save energy. So it's not just static, dynamic versus code, but there's the question of the context, and beyond that, there are design techniques that you can use that will assure things on down the line. So let's not just cast this as static versus analysis. There are many more points at which the analyses can be done, and so all the analyses should be done as early as possible, but no earlier.
Since JavaScript came up several times today and it relates to this, I think I'd like to sort of also drag into the context the whole question of why this vast movement has occurred from languages that have well-known type systems that are checkable at least partially statically to these dynamic languages like JavaScript, which are extremely difficult to check. And I think the challenge there is that developers find something in these languages, whether it's small startup cost or greater productivity, that they don't find in the other languages. And that, to me, is a challenge that's worth going back and reinvestigating, which is, what makes these languages so attractive that people are willing to give up things that I think are very, very valuable, like type checking. As someone who's written, tens of thousands of lines of Lisp code, I pined for something that would actually give me a guarantee about that I wasn't going to have, an integer added to a string. So, again, this is something that is very difficult to do if you're in the middle of developing something commercially. But this is the community that should be answering this question. And I would love to sort of see this dynamic static expanded beyond just the question of when these analyses happen to why people want them to happen that way and what advantages are they getting from deferring things until runtime.
Oh, could I add one thing? I got trapped into the assumption of your question, which is the thing that should be analyzed is the code. These large systems are chock full of things other than the code. They're full of models, 3D models of things to be displayed. They're full of data. And a lot of the integration problems that you run into are actually ontology mismatches in the data structures themselves. So I want to make a short appeal for extending this contemplation of analysis and validation to all that other stuff in the system besides the code, especially the data.
All right, so you're talking a lot about codifying engineering. You're talking a lot about codifying engineering. And I think as software engineers, it's our duty to take one step further than what the engineers did before and have that codified. I mean, our knowledge should be machine readable such that it is usable by our software. So if we look at current software engineering, we produce textual documents all over the place. It's full of terminology, it's full of words. These words have special meanings in our context and our domains. But our machines are really poor at dealing with these things. And a lot of it has to do with their lack of context. So it'd be nice not only with the codification of our engineering, that we also have it machine readable such that the machines can understand the context of these textual documents. I was wondering if the panel has any ideas related to this topic of context and machine readable domain knowledge and engineering documents.
So since I have the microphone, I'll start. I don't want to criticize the organization of this day, but it seems to me that the discussion here has left out what I consider to be the most important part of software engineering and software development, which is the people. That, the problem with what you suggest is that if we make things less readable by people and more readable by machines, then we exacerbate a already difficult problem, which is that a lot of errors and a lot of problems in software development are caused by lack of understanding and lack of interaction among the people who are doing the development in rather large teams of people. And so, it's not an easy choice to say just make things more formal, because at the same time you make them less readable.
There's online and there's online. The classic engineering handbooks, I think about Perry's Handbook of Chemical Engineering, which is 9 by 12 by about 4 inches thick and printed in 2-point type on Bible paper. This has the body of knowledge, but it gets reissued about once every 10 or 15 years. Okay, this isn't good enough for us. I'm in favor of having that kind of organized, systematic reference knowledge online, because that's the way we get to information these days. But that's online for access by people. And Jim was suggesting that you might have meant online for access by automated analyzers. If that works out, that's nice, but I think getting it accessible to people is most important. There was a third case that has just slipped my mind. Offline.
Joe, did you still have a comment?
I actually, back in your
So is this the same? I think it was Mary's comment about when we moved to high-level languages, people couldn't write loops in a billion different ways, and maybe that wasn't such a bad thing either. I'm sure there were interesting loops that people wrote before we had structured.
Right.
I wrote a lot of them, but I only needed 10% of them.
Right. So I'd like to say this isn't specifically scripting languages, but it addresses the issue that's sort of come up several times here about, modern high-level languages with all kinds of, checks built in and so forth. So you simply can't make a lot of the same kinds of mistakes. And, I've been hearing this for a long time, and I remember, about the time I finished my PhD, we had this wonderful language called Ada, and then eventually, we had Java, and we had this, that, and the other thing. But so much code out there is still written in C, and 20 years from now, will still be written in C. That's my, a lot of this is about prescription, but that's my prediction, okay? And it will still have the same bugs it's had, for the last 40 years or whatever. And I don't think that's going to change. And scripting languages, the new code written in scripting languages will often have a lot of the same bugs, but maybe different ones. But we're still going to have that same old problem of that old C code, and that isn't really going away.
So I think I like a language because I can fiddle around in it as kind of self-indulgent, because it doesn't respect the implications of having idiosyncratic code that's going to be there 6 days, 6 weeks, 6 months, or 6 years from now for somebody else to maintain. On the other hand, maybe not. On the other hand, there are languages that are not full-blown, strongly typed programming languages, which sometimes are too strongly typed for their own good, I would add, but that capture the abstractions of a particular domain. So there are a number of domain-specific languages that have crafted notation, sometimes graphical notations, for particular problem domains that bring the level of discourse closer to the problem domain and to the experts in the problem domain, and that provide fewer opportunities for gratuitous fiddling around that leads to errors. And those, I think, we should give a lot of credit for.
Yeah, indeed. I've been looking at a few domains that you could think of generally as sort of the e-science kinds of domains, where people are trying to compose fairly interesting computational systems, analytics and so on. And when you look at the things they have to write, it's really awful. These horrible scripts and glue code and things that are almost impossible to debug or to maintain or to even reuse. And although programmers might really want to have that kind of flexibility, it seems like most of the world, the 90% that Mary mentioned in terms of end users who are actually having to take advantage of computation for their profession, not because they're professional programmers, they actually really would rather work in a much more constrained world of either domain-specific languages or tools that really guide them towards simple solutions to what they want to do with the analytics that actually make sense to them in their field.
I'm sure the number is true, and I think the answer, you said it, which is that every browser in existence supports JavaScript, and you can do things in it in terms of building user interfaces that you can't do in HTML and CSS, and so everybody does it. Barbara?
something like that that constrains the use of some of these things for the maintainability of the code, but I have no evidence,
So-
from real life that that's what's going on. But you
So-
see that kind of
so-
differentiation across some of these sites, and it's just too, it's just so visible. I don't think it's random. I think this is practices in companies, or you shouldn't do this, you should do that, because that can lead you to.
You don't have that constraint even just within.
In some places, yes, but in others, no.
So a lot of JavaScript is also generated as the assembly code out of tools. So Steve Lugo talked the other day about TypeScript, which is Microsoft's typed subset of JavaScript, which generates fairly unexciting JavaScript code.
Well, based not on looking at any of the JavaScript, but based on looking at a lot of the websites in question, it seems to me that a great deal of that code is really doing state transitions about the web page. You do this and the page transforms in the following way. And JavaScript seems to me like a really poor substitute for an actual state transition description language, and perhaps describing those web pages in something that lets you think about the states and the state transitions rather than something that can be mapped back to them if you decompile it would be a step forward.
I'd like to resonate with some of these recent comments in saying that we're looking too low level, that today's big systems are built out of components that are written out of low level stuff, but they're written in glue code. Or for example, that Lori was showing the power of a workflow model, and there's really a lot that could be there if we're not looking at that. And if you look at any of the good things today, we started with Angry Birds. That's written in Dua. I didn't hear anybody mention anything about the semantics of that language, or Scala or Django, or any of these. But ultimately, we're talking about components that are composed, and we like the scripting languages because they're easy to tie together stuff that we didn't write. And we need to be looking at it as a community, because I think that's where the future is and where many of the problems are.
Let's do one question, last question.
This is, I'm Julius, by the way. I'm at UBC. And I just want to bring us back to all of software engineering. I want to tell you something I saw once, and it goes back to what Gail was saying about we're never going to get it right the first time. And so I went back to visit a company that I'd worked for several years, and I walked into the developer area. There was about 20, 30 developers in cubicles, and then there was the wall, and behind the wall was the manager's office. And above the manager's office, on this wall, they had printed a huge banner. And the banner said, "Get it right the first time." But there was a little square of paper taped to the banner right after the word right. So "Get it right," little square of white paper, kind of, you couldn't really see it from far away the first time. And so I asked one of my friends who still worked there, I was like, "Why is there a little white square of paper on your banner?" And he said, "Oh, well, there's a comma under that square of paper." And I think that thing is like, it's the funniest and the saddest thing I've ever seen. And it's so apt.
So I'd like to abuse my power here and ask the last question. In several of the things that were mentioned today, in particular in the panel, I heard an overtone of thinking about code at a higher order, thinking about higher level abstractions, something Mary said particularly resonated. So the question that I'd like to ask is, do you see a resurgence of architecture research in the near or far future?
Can either of you address that, please?
So, well, there are two places where I think architecture is particularly important. One is in the runtime setting. So we've always thought about architecture as something that happens at design time, and it's there to assist us in making, for example, quality attribute trade-offs. But imagine that you had a system where you had some knobs that allowed you to make those quality attribute trade-offs at runtime, doing on-the-fly architectural decision-making, for example. That's a very different thing, but it requires models of architecture, but a very different set of mechanisms. So that's one example. The other one is in the end-user communities. I think many of the people that actually do composition in their own professions are really being more like architects than programmers, or would like to be. They want to compose pieces, and they want analyses similar to what architects want, namely performance, security, privacy. That's what they really want. And the scripts are there just to get them by to do that. So again, I think there's another way of looking at architecture in terms of raising the level and in some sense making it more domain specific so that people who are not trained software engineers can actually use that.
Certainly wouldn't want to go before those two. I actually think architecture is incredibly important to getting software right. I mean, I think that's sort of a truism, but it's one of these concepts that many people seem to come out of school without really believing and understanding that. I mean, I've never had more difficult discussions at Microsoft with software developers than discussions about architecture. You know, they just do not seem to have learned this at some point in their career, the importance of getting the architecture correct and what you could do about it, how to talk about it. And I think it's very unfortunate, particularly, you know, I've been moving into new areas, things like cloud computing, where a lot of what's going on is people are trying to define what the effective architectures are. And what you see is this tragedy of CTO after CTO of these little companies producing decks talking about, well, we did it this way and it didn't work for these reasons, and then we did it this way and it worked until we got 10 times more customers, and then, you know, and they all are following down the same set of architectural steps, but nobody is able to step back and sort of talk about it as an architectural problem, that they're all trying to solve the same problem by building scalable, efficient websites. And, you know, I think that the idea is there, and they all realize the sort of importance of it, but they don't have the vocabulary or the abstractions to talk about it. And I think that's really too bad because, you know, particularly in a new area, you get to see architecture being invented and people thrashing around trying to understand what it is they just did.
I resonate with your statement that a lot of the people you talk to don't have a sense of what their architecture is. I think a lot of this is a result of the development tools that implicitly lock you into some particular architecture. And then you wind up defaulting into that architecture because that's the tool that everybody uses rather than actually thinking about what would be a better choice.
Yeah. Okay. And on that note, we will transition to our closing session. Let's thank the panelists. So if I can ask my co-organizers to come up. So we would like to conclude this by a certain call to action. We spent all day today talking about different kinds of problems, different kinds of progress that has been made in various groups. And so let me just start out by summarizing some of the big ideas and big problems we've come up with. The first problem is what's in my pocket. So we talked about, several of the speakers talked about how to use humans better in our research and in software systems. So there were three different areas in which were touched. One is how to understand developers better and how to build tools that work better with the developers. Another point that was touched on was understanding the users and being able to verify that what the users are doing is actually what you expect them to do and what the system expects them to do. And then finally, there was some work on using humans as tools, as part of the software systems to actually either prove something about the software system or advance the software system in some way. So some of these are not necessarily new ideas, but there's new problems that have been identified in those areas. But lots of things with humans. That's something to walk away with. Another thing we talked about today is software quality. So people have talked about security and doing that from a very scientific point of view. How do you ensure security happens? We've talked about assurance of large systems. Assurance is hard. We don't know how to do assurance for any kind of a complex system, so lots of open problems there. We talked about doing outside the box analyses, different kinds of analyses, things, again, that use humans, things that blend different kinds of analyses that already exist out there in order to be able to prove or verify different things about your system that were possible before. And we talked about improving the quality of the system in an automatic way by using variants. generating automatically lots of versions of your system and trying to be able to improve something about your system that way. Okay, the third point here is there was quite a few things with code generation. So PowerPoint decided to create a variant. So with code generation, we talked about using code structure and the repetitiveness of code in order to automatically be able to generate programs or be able to fix existing programs. And we again also talked about using variants to improve the system quality. So mutating the programs automatically to create a system that's better than the original. And then the final point is there were several application areas that were brought up. There was healthcare, and I actually expected healthcare to be a really big topic of discussion during the panel. It didn't happen to come up, but there's so many different problems in healthcare, from things that Lori talked about on trying to understand how humans interact in the healthcare system, to things like we want to build systems for the healthcare system to use. We don't have electronic health records still. It is beyond me why we still don't have electronic health records. As far as I can tell, all the technology is there. So what's missing? Why haven't we done that? So lots and lots of problems in the healthcare domain. We talked a little about elections domain. We've talked about the new problems that are brought on by multi-core and by cloud computing. And we also talked about user interfaces and how those need to change pretty dramatically in order to achieve some of the big goals that we have. So these are some of the big areas, big questions we've identified today. Now, this is a one-day symposium. This is not intended to be a complete list of all the big problems and all the big advances that will happen in software engineering in the next, say, decade. It's a subset. It's representative of the people who spoke today, and there's certainly other problems. But I'd like to take this opportunity to encourage the students to think about some of these problems. Don't limit yourself to these, but think about these. Think about what you can do in some of these problems and some of these questions in your next 4 or 5 years as you're getting your PhD, some of you. Not because you're very fast, but because you're almost done. And see if you can get us closer to the future, because it's going to be you doing all the work. It's not going to be old geezers like me. Would you? I can't say that yet?
No.
Okay, sorry. Okay, I'll do. Okay, now that I've been put in my place, would you guys like to add anything?
Go first, Mike.
So I think there were, in addition, this is a really nice summary of what we talked about. I think one other cross-cutting theme that I heard was trying to think about costs. So all of engineering is about balancing costs. And we can think of these in those terms too. For instance, for people, should people be doing the work? Should tools be doing the work? How should that be balanced? In terms of quality, what are you willing to pay? In terms of the programming language we talked about, are you willing to pay more up front in order to pay less later, or the opposite? And which one of those makes sense? What we want to do is to not make random choices. We want to make disciplined choices about these. And I think that's one of the biggest challenges we have. I think the issue of how to use people is incredibly important, because what makes our discipline so difficult is that rather than if we were analyzing, say, a mechanical system, we have non-ideal components, nonlinear components in our system. They're called people, and if only we didn't have to deal with those, our field would be much easier. We get all of the difficult mathematical challenges, and we get all the different psychological challenges, and we're trying to balance the costs of those and blend those together. I think that's what makes our field one of the most exciting in which anyone can work, and gives it tremendous potential to affect the world. Another thing that I saw that I wanted to bring out is trying to think about problems in a different way, or about different problems. So what I heard people saying is, we don't just want to think about what are the old problems and how can we solve those a little bit better. What we want to do is to cut the Gordian knot of complexity. Say, here's a completely different way of achieving what your real goal is, or what your real goal ought to be. So don't just think, here's something that people are doing in a non-optimal way, or here's something that people are doing slowly. Can I help them do it faster? Think about how can they help them to do something completely different, because that's how you're going to disrupt the current processes of software engineering and make them much more effective in the future. So I've really enjoyed hearing all of those ideas and many more that can really inspire all of us.
Right, so it's lovely to have the last word here. Thank you very much, Yuri, for the what, and you, Mike, and also the why. So I'll do a little bit about the who and the where. The who, of course, is you. You're the people who are going to have to take this out and do something about it. And once again, I'd just like to say how delighted we are, now everybody is, that we have such a great turnout here. Where are you going to do it and when? So there are various ways. The one is do it in collaboration. And we've heard on and off throughout the whole day that if you're going to tackle the big problems, you have to do it in teams. And some of those teams definitely need to include places outside the institution you're at. So team up with other universities or industrial institutions if you can do that. So some of the examples that you can use for that are the CEF Awards that Microsoft Research offers, and they'll be coming out again in October. Keep a watch for those. We'll try and notify all of you if you don't mind us using your email addresses for that notification. And also, ICSE has a Future of Software Engineering workshop, doesn't it?
A track, yes.
Yeah, a full track upcoming. So that's another thing to follow up on that you can look for your research, actually, to publish it. And we did talk a little bit about publishing research. That's in the long term. In the immediate term, like in the next 5 minutes, I think that we can continue this discussion, and there's no better way than continuing it over a good glass of Northwest wine. And our man over there in the tie-dye shirt, Chris, has arrived in time, and he'll be directing you all in a nice little stroll over to Building 99, where everything is ready and set up. And please enjoy yourselves this evening. Can we make sure that those of you with special eating needs go to the front of the queue for the food once the food is out? And have a wonderful time tonight, and thank you again.